All right, let's talk about apparent power. And you're like, what the heck is apparent power? Well, in reality, when power companies deliver power to different facilities, not so much residential, just because it's such a small loss. But we're gonna learn that there's an apparent power and a real power. So the real power is what you actually use. The apparent power is what it appears to be drawing from the power plant, right? Because because of the phase angles, you wind up with different loads, like inductive or capacitance loads, winding up drawing extra power to make them work. In short, that's the basic. That's really not a very accurate description, but it's the basic description. But you can get this this power by. So we got the voltage, the RMS voltage. Oh, I gotta start. Oh, I am recording. And the current, the RMS current, right? And remember, these are the root mean squared versions that we found in the previous section. Oh yeah, here it is. Recall for sinusoids, right? For sinusoids, the RMS is just the max voltage divided by square root of 2. The same thing for current, right? So if you wanted to do this, you would actually have S equals, in fact, this is in your textbook, S equals 1/2 VMIM, because, let's see, there's a list of formulas in your textbook. Where is that? I know I've seen it before. Oh, they have it in terms of regular power, VMRM. Yeah, but you've seen that before. Notice, right? There's going to be a phase difference between voltage and current. Well, there's usually a phase difference between voltage and the current drawn. If it's 0, it's just 1. And this is what's called the power factor. The cosine of this difference is the power factor. It's basically the the real power you're drawing divided by the apparent power. And this power factor is always between -1 and 1, because it can be negative. I mean, the absolute value of it is between 0 and 1, but it can be negative, and we'll see that in a minute, right? If you've got the theta V less than the theta I, right? So if current leads voltage, it's negative. If current lags voltage, is positive. And we'll see that in the next couple of slides. Yeah, just so you remember, this is from earlier. In fact, I was looking through the slides. I don't know if this is actually the slide deck as it is in your textbook. I think there's section 11.4. But the average power, right? And we did this in one of the calculations we made. The RMS voltage, RMS current times the cosine of obviously the difference between them. This shows up as VRMS I star, right? Yeah. Why is it called apparent power? Well, because that's what it appears to be. That's what the power in the circuit appears to be. So that's what the circuit appears to draw, that much power. And you've all got a power meter on your homes, right? And it's basically measuring the power that you're drawing to your house. It's measured in volt amps, so VA, to distinguish it from the average or the real power. So we use VA as that unit for apparent power. Power factor angle, we just discussed this, right? The power factor angle, it's equal to the angle of the load impedance. So if you have a load, right, and voltage is the voltage across the load and current is the current through it, well, by our formula, right, V over I, you've got to have V minus theta, or theta V minus theta I. And we'll see this again in some examples. Here it is, power factor from 0 to unity. Again, it's the absolute value of that, where it can be positive or negative, right? So when they say 0 to unity, it's plus or minus 1. So as I was talking about, right, if current lags the voltage, it's positive, and vice versa for negative angles. Remember, current lagging voltage means this is smaller than the voltage of the theta voltage, and opposite is true, right, for negative values. A purely reactive load, so just pure resistors, if everything's just a resistor. And again, that's, well, most of our household items, we don't have a large inductive or capacitive load. And so mostly it's reactive load. And the power factor, because actual industrial sites have higher reactive power, this is a really good video. What I did is I put this video in the supplemental videos, Power Factor Explained. I want to say it's like 10 minutes. It's actually not that bad. It goes through basically the rest of this chapter from here forward. And it explains it using, it gives you some real world examples. And they also explain, I like it because, well, I don't necessarily like it, but they explain power factor and with respect to beer and the foam on beer. I'm not a big beer person, but if you are, then, well, you guys, most of you shouldn't be drinking it, right? All right, practice problems. Let's do some of these. And this is hopefully where we'll see some better information on power factor and reactive power or apparent power. All right, obtain the power factor and the apparent power of a load whose impedance is 60 plus J40 ohms when the applied voltage is 155.56 cosine, this number right here. So we're going to do that one first. Oh, let me shut my blinds. It always happens on a Monday, Wednesday, Friday. I'm so tired of the dark in my office. At the end of the day, I open the blinds. All right. We want to know the power factor and the apparent power of a load with a given impedance. So let me just sketch this out first. We have an applied voltage. And I'm not going to rewrite the whole equation here because it's not that critical. I'm just sketching this out as a visualization. This is going to be the load. Z is 60 plus J 40 ohms, right? Now, just taking the Pythagorean theorem and finding the angle and the magnitude, you can also write Z in phasor notation, right? 72.11 angle, 33.7 degrees. Yeah, that's a degree sign, not a zero. Now, the power factor, if you recall, is cosine of theta V minus theta I. Oh, I should have used lowercase. V here, we can rewrite V as, if we work in the frequency domain, we've got 155.56 angle 10 degrees, right? So recall the current is equal to the voltage over the impedance, right? Or V equals IZ. I mean, that's where it came from. So we've got these two written in phasor form. So we've got 155.56, because I'm trying to find the phase angle of the current. And you can see what it's going to be here. You just, you're just going to be 10 minus the 33.7. Got 10 degrees. And then we've got 72.11. 33.7 degrees. This gives us a current of 2.157 angle negative 23.7 degrees. All right, so we can see what theta I is. Where's my calculator? Oh, there it is. I'm going to probably need it in a minute. All right, so this is theta I. So the power factor is cosine. We got 10 minus, you can see this, but I'm just plugging the numbers in so you see where everything's going, where everything's coming from. All right, so basically 10 plus 23.7. You've got the cosine of 33.7. Oh yeah, that's pretty close, 0.832. So the power factor is 0.832. Now, if you don't want to remember, positive is a lagging. Remember, we always refer to, well, we typically refer to current versus voltage, right? Is current leading or lagging voltage? So we say this is, well, I could write current lagging, just so we remember. But when you're asked if it's leading or lagging, right, it's current with respect to voltage. And a few things here, right? This is because power factor is positive, right? That's, or you can look and see that theta V is greater than theta I, right? In both scenarios, this tells you the current lags voltage. So that's the power factor. So, you can remember this, positive is current lagging, negative is current leading. Or, you can look at the theta angle. Sometimes you might not be given both theta angles. You might just be given the power factor, and I don't know. You'll have to know, okay, is this a current leading or lagging? And that's just positive, negative. All right, let's call this part A. And then let's look at part B here, which is finding the apparent power. Find S, apparent power. So this is the basic equation we have for S is VRMS times IRMS. You can see the magnitude or the maximum, right? This is basically the same thing as, let's write this out, Vm over square root of 2 times Im over square root of 2. And this is going to be 1/2, right? The square root of 2 is, what do we got? We've got 155.56 times, there's the, 72 point, oh wait, not, we're looking at I, current. There it is, 2.157. So this turns out to be, should be 2.157 times 0.5 times 1.6. Yeah, 167. Yep, 167. I'll round it up. 160. I'll go to 168. Oh, sorry, VA. So that's the absolute value. You could also write this as a phasor, right? 168 angle, 33.69. Trying to remember if look at the example next to this 11.9. Oh, that's capacitance. Yeah, so that's your apparent power, the 168 VA. We're gonna talk about the angle when we talk about complex power, so you'll get a taste for that. All right, 11.10. Calculate the power factor of the entire circuit as seen by the source. What's the average power supplied by the source? So now we've got, this is in the context of a circuit, right? The first one was just basically plugging, chugging the formulas. All right, the first thing I want to do here is I want to take this circuit, I want to figure out the overall impedance. So overall impedance of the circuit. So that's going to be Z is going to be equal to, now let's look at what we got here. We got this 10 ohm resistor, right? And then we've got this branch that's in parallel with this branch. Recall, I mean, we're sort of given the information here. I just want to draw your attention to this, this really quick here. The impedance, right? Remember the generic formulas. If you're given a capacitance, you're going to convert it to something like this form, right? Negative J6, right? The negative J is just 1 over J. So that's where these come from. These come from taking a number like that, or taking a formula like this, right? Z equals 1 over J omega C gives you this. So you could back out the capacitance by solving this equation if we knew what omega was, right? We don't know omega. So it's very helpful to be given this stuff in this format. So you can just deal with it without having to convert it into individual impedance values with the formulas for inductor and capacitors. Anyway, these two are in parallel. This one's in series. So we're going to have 10 ohms, right? Plus, we've got J4 is in parallel with 8 minus J6. Parallel, not 11. So let's see, Z is going to be equal to 10 plus, we'll have J4 times 8 minus J6 over J4 plus 8 minus J6. This is going to get us 10 plus. All right, what do we got? We got J32. Let's see, that's a minus times a minus is going to be a plus 24 divided by 8 minus J2. We can take this and do our little complex conjugate trick. Oh, you know what? Let me factor out a 2 here. We're going to have J16. I'll rearrange this. 12 plus J16 over 4 minus J. I'm going to take this. I'll put a 1/2 here, so you know. Well, I'll factor out it. Yeah, just ignore it. I just divided by 2. Factored out the 2. Oh, that's what I was going to do. Yeah. This is 4 plus J over 4 plus J. You know, it's one thing to sort of go through this Again, I'm trying to show you as much detail as I can with the complex numbers, because I know it's not something that you normally deal with, right? But once you do the homework, I mean, at this point, you should be fairly comfortable dealing with the complex numbers. This is going to be 10 plus, we're going to have 32 plus J17. I skipped a step here over 17. So you just do the algebra, you're going to get this. So Z equals 11.88. I'll just stop at this plus J 4.47. This is also equal to 12.7 angle 20 point. Let me just check I'm rounding my numbers a little bit. 4.47 divided by 11.88. Yeah, 20 point, well, yeah, we'll do 20.6. This is what Z is. So we haven't actually solved the problem yet, but this is just to get to the point where we can solve the problem, right? So now we have a voltage source and an impedance. This is Z, and this is our voltage 165 angle 0. Draw a line there. All right, so that's what we have. Recall that the power factor is cosine theta V minus theta I. Few ways to look at this, right? If we calculate I, it's just going to be V over Z, right? It's going to be 165 angle 0 over 12.7 angle 20.6. That's 13 angle minus 20.6, right? So theta V is 0. Theta I is minus, oops. How did I switch angles? Hold on a second. Let me just, yeah, it's 20.6. I don't know where the 26.8 came from. Minus 20.6. All right, so the power factor is going to be theta V minus theta I is going to be cosine of, again, positive 20.6. Now I'm doubting my numbers because, yeah, all right, I have a typo in my notes, or a write-out. .936. So power factor is 0.936. This is lagging. Now, I mean, you could have easily looked at this, right, and done this part in your head. Said, okay, well, oh, that's what I wanted to show you too. The impedance is 20.6, right? So theta V, or sorry, this in here is going to be basically the negative of that, right? Voltage divided by the impedance. Let me see where that was in the slide here. Angle of the load impedance if voltage is across the load. Oops. Oh my God, my phone is talking to me again because I don't know, I got to turn off Google somehow. All right, sorry about that. I got distracted by my phone. And it's off too. Well, it's in airplane mode. So what I wanted to show you is, I wanted to show you that slide, right? There it is. This is equal to the angle of the load impedance, right? So the angle of the load impedance is 20.6 right here, right? Notice theta V minus theta I gives us 20.6. So you didn't even have to technically do this calculation. You could have just looked at the angle of the load impedance and said, okay, 20.6, that is the angle in here. Take the cosine of that to 0.936. All right, what's the average power? That's the power factor. Let's do average power here. The power is going to be VRMS, that's a V, times IRMS, times the power factor, which is, I'm going to write it out, cosine theta V minus theta I, right? And we can see this is the power factor. And this is actually S. So this is the apparent power. So what do we have here? We've got 165. That's the voltage. The current, we have 13. All right, I'm sorry, I have to shut my phone off. It's driving me crazy. All right, hopefully that'll stop. Oh, the power factor here is 0.936, right? So what's this telling you? This is telling you this is the apparent power, right? We've got a power factor of 0.936. Our average actual power is going to be less than our apparent power, right? So our power is average, let's put average down here, 2008 watts. Watch your units. These are, I mean, I was kind of sloppy about my units, right? These are volts. This is the amps, right? Because we're working in volts and ohms. So just be careful. Like, you know, I sort of knew this problem, right? We're working in volts, we've got ohms, we don't have kilo anywhere or micro, right? So I don't have to worry about converting numbers from one to another. This is the average power, 2008 watts. The other thing I want to show you here is Z. Where's Z? Z is equal to 11.88 plus, this is an aside now, J 4.47, right? This is the resistance component, and this is the reactive component, right? And this shows up when we have capacitors, inductors, etc. If I just write out the power as a function of just the resistance, I've got I squared, or IRMS squared times R. I wind up with 13 squared times 11.88. 13 squared times 11.88. This should give us, yeah, it's like 2007.72. So this is also about 2008. I mean, I rounded in all of these. Right, so this is basically what it's telling you is, or what I'm showing you here is the real power, right, is a function of this resistance load. The reactive is what contributes to the apparent power, right? The reactive resistance, so things caused by capacitive or inductive loads. And that's what you're going to see. We'll see this again, but also you'll see it in the video. They'll discuss some of, well, that's primarily why a lot of industrial locations have a really poor power factor, is because they've got a lot of reactive load, right? So think about, they've got a lot of three-phase motors and you know, large industrial equipment, that has capacitive and inductive loads to it. All right, so that's this example. All right. Oh, what am I doing? We did those. All right, so this leads into complex power. So complex power is talking about the total effect of all parallel loads on power, right? So complex power, this is this vector S now. It's so difficult to know the difference between these letters if they're they're just using a bold or not. But the complex power is this 1/2 V complex conjugate of I, right? And you can also use the RMS values again. I squared Z, right, is also V squared RMS over Z star, right, which is the same as V RMS, I star RMS. So this is where the 1/2 comes from, right? If you take the RMS values, you get VM, IM, both over the square root of 2, which gives you the 1/2. So just remember, if you're using the magnitude of the voltage, right, versus the RMS of the voltage, there's that square root of 2 function underneath that goes between them. And complex power, if you look at complex power in rectangular form, right, you can draw these triangles. And these triangles represent a few things. So we've got first, let's go back here for just 1 minute. See this, we're working off of this I squared RMS Z, right? Remember, we talked about Z having a real or a resistive and a reactance component. And if you look, you've got the I squared RMS times R, right? This is power. This is what we're used to as power. Plus, you've got this X times I squared RMS over here, which gives you this Q. So Q is this new term. P is the average power, or the real power, right? Notice on the axis here, P, right? It's on the real component. It's the current times the real component. And then Q is this component up here. This is the reactance. The reactance power, or reactive power. This is the power that's either, again, positive. It can also go negative down this way, depending on if it's an inductive or capacitive, right? Because you can have Z is R plus JX or Z is R minus JX, right? And that's going to determine the direction of this reactive power. Let's see. Oh, this is just showing you, right? This is Z, the magnitude of Z, which is a combination of R and X, and you wind up with this triangle and you multiply. So the only real useful measurement is the real power, and that's measured in watts. The reactive power is basically, energy exchanged by the source and some kind of reactive load, like an inductor or a capacitor, right? That's the power that we're not really getting anything out of. It's sort of like, it's like it's non-useful power. We're not actually using that in the to do any type of work or anything. And if you look at the quadrants, we're either going to be, like I said, we're going to either be a positive or we're going to be a negative, right? And these are, when you have inductive loads, you're up in this region. When you have capacitive loads, you're down in this region, right? So you have a positive angle, theta V minus theta I, or a negative angle, theta V minus I. So this is a good drawing to sort of keep in your head. Again, the imaginary, the real axes, right? Pure resistive loads are always along this real axis, right? Because they have no J component. Oh yeah, this is just a summary. This might be a good reference sheet for you to have. Let's see, complex power, blah, blah, blah. Yeah, these are all summarized in your textbook as well. I think I just decided to make a slide for it. Real power, reactive power, yeah. All right, let's do some practice problems here. I think we'll definitely be able to make it through this chapter. All right, practice problem 11. Oh, you know what? Let me just read it on here first. We have a load. We're given the RMS voltage, and we're given the RMS current. So we're not told the load. Determine A, the complex and apparent powers, the real and reactive powers, and the power factor and the load impedance. We're going to be able to use this equation right here first, because we're given the voltage and the current RMS, right? So if we want to find the complex and apparent powers, we can use, for the complex power, we can use this formula, right? And the apparent power is just going to be basically the components of that, right? Notice the magnitude signs, right? VRMS, IRMS, the magnitude of VRMS, the magnitude of IRMS, and then their phase angles. And then you can just take, for the apparent power, you can take the, you're basically looking at the triangle, right? You're looking at the hypotenuse of that triangle right here, S. So let's look at the, all right. I should have printed that slide out. So let me write complex power with a vector sign, because I can't write the boldface. So the complex power is just the RMS voltage times the complex conjugate of the RMS current. Now, I mean, you could convert this to J form, or to rectangular form, and you could take the negative of the J term, or you can just recognize the negative of the J term flips the angle, right? J plus, oh wait, R plus JX to R minus JX, right? This is just a flipping of the angle. This is going from something like this to something like this. So what do we have? We've got 110 angle 85 times 3 angle minus 15. Right, that's the complex conjugate of the current. So for S, the complex power, you get 330 angle 85 times negative, well, times multiply, you just add them, so you get a 70 here. And this is VA. So this is the complex power. This is what I accidentally wrote on the other the other problem when I put the angle in. I didn't intend to, but I had forgotten we hadn't done complex power yet, or we hadn't talked about it. The apparent power just the magnitude of that, right? Go back to the slide here. It's actually right here. So I mean, you could take each of these individual ones, the magnitude of them, and multiply them, but you're going to get the same thing, right? It's basically the 110 times the 3, so it's without any of the angles. So the apparent power is 330 VA. Complex, apparent. Now you know why vectors are so important. They're kind of used in every subject. The real and reactive powers let's look at this. We've got S, the complex power is 330 angle 70 VA. Now, instead of just writing out the values, I want to show you, right, what it looks like on the real imaginary axis. Oh my God. All right, draw some straighter lines than I did. Real, imaginary. We've got 330 angle 70. So this is something like this, right? So our real component runs down here. This is P equals S cosine 70, right? This is the magnitude, right? That's all this is, right? Complex power is just the magnitude and the angle. And then the reactive power is going to be over here. That's the sine, right? Sine of 70. So we can figure these out. We're going to put this for the 330. I have power first. Cosine 70. It's going to give us 112.9. And remember, the real power is in watts, right? That's right along this axis here. And then Q is the reactive power. Let me just put in parentheses real. So the reactive power is going to be 330 sine 70. All right, so it's going to be 310. I'm not going to even round to the decimal. And the units on this are VAR. VA reactive, right? So this is VA. The real component's in watts, and the reactive component is VAR. So this is reactive. So if you're given something VAR, that's the reactive power. The watts is the real power. And then it wants to know the power factor and load impedance. Excuse me. Oops. Power factor is cosine theta V minus theta I. It's also equal to the power over the apparent power. Now, there's two ways to do this, right? There's multiple ways to do this. You can look and you can say, okay, let me just write this out. We know that P is S cosine 70. And S is just S, right? So these S's cancel out. And you wind up with the power factor is just the cosine of 70. Right? Alternatively, you could recognize that, oh, you know what? We're given the voltage and the current. Theta V is 85. Theta I is negative 15. Oh, sorry, positive 15. That's the complex conjugate. We got to take it from up there. Theta I is 15. So cosine theta V minus theta I is equal to cosine 70. Right. So either way, you can get this. I'm just showing you the, some of these equations here that we can use. Power factor, right? power or real power over the apparent power, right? So either way, you wind up with the same cosine 70. So the power factor here is going to be 0.342, 0.342, and this is lagging, right? Current is lagging voltage, and it's also a positive power factor, so we've got that working for us. Oh yeah, load impedance. Let's go back to the slide here. Is it on this? It is not on this. Well, we know what load impedance is. Load impedance is just VRMS over IRMS. 110 angle 85 over 3 angle 15. Right? We have this information, V over I. We know what the load, we know what the voltage is and the current is for that load. So we just use the the impedance formula. I'm gonna round to 36.7 angle 70. So Z is the load impedance. This is in polar form, right? You can also write it as rectangular form. So you can see the real and the reactive components. So what I got, 36.7 cosine of 70 gives me the bottom, so 12.6, I'll make it. And we know the angle's positive, so we're going to go upwards. 36.7 sine 70. It's going to give us 34.5. We'll go with. I like to put the parentheses sometimes for. Well, that messed it all up. So that's how you can write the load impedance, right? You can write it in either rectangular or polar form. It just occurred to me I've got to specify how to enter that in the final exam questions. Were there any questions about that particular problem? I keep forgetting to ask if there's any questions. Let's go to 1112 here. We've got a sinusoidal source supplying reactive power. So this time we know what the reactive power is, 100 kVAR. And we know what the load is. Z is 250, well, the impedance, right? 250 angle negative 75. Find the power factor, the apparent power delivered to the load, and the RMS voltage. So kind of similar to the last one, except kind of backwards, right? First of all, the power factor. Remember, the power factor can be found by either taking the difference between theta V and theta I, or looking at the load impedance angle. And why is that? Recall, Z is V RMS over I RMS, right? So this gives you some number. We'll just call it VM angle theta V over IM angle theta I, right? So that's where the theta V over theta I comes from, or theta V minus theta I comes from, right? So the impedance, that's why you can just take the impedance angle, right, the load angle, and just substitute it in. So we're going to take cosine of negative 75. Oops. So 0.259, we'll say. Now, this is a leading power factor, right? Because our angle is negative. Leading. Now, I forgot that your book made a mistake here. It's not the actual cosine, obviously, because the cosine of a negative angle is still positive. And I'm trying to remember where it said that let's see, power factor, cosine angle. Hold on a second. There's some mistake in the, that's where it was in the slide, I think. Leading, lagging. Yeah. Here it is. Power factor, it's a negative angle. Yeah. Purely resistive. Here it is. Yeah, you've got to look at the angle. I forgot about that, and then I was just going along with it because I've forgotten that the cosine of the fourth quadrant is still positive. So theta v minus theta I is negative. I'll correct that in the other example problems. So this is a leading power factor, right? So current I leads V. I knew there was some mistake in this chapter, and I couldn't remember what it was. And that's what it was, the leading, lagging, or the negative part of the power factor. All right, so that's the power factor. Let's look at the apparent power delivered to the load. And we're given 100 kVAR is the reactive power, right? So we're given reactive power. (100 kVAR). And we also know theta V minus theta I, right, is a negative 75 degrees. So I'm going to sketch out my drawing here of the real power, which I don't know, right? I'm not given that. This is my reactive power. This is 100 kVAR. And this is my apparent power, S, right? And this is 70 degrees. So if you just look trigonometrically, right, Q is equal to S sine of 75, right? Obviously, it's the negative. So we can find that S is just Q divided by sine of 75, which is 100 divided by sine of 75. You can put the kVAR up here, kVAR. Did I? Okay, I didn't forget that. And you wind up with S is equal to 103.5 kVA. That's our apparent power. I'm just going to check the math here. Yeah, well, okay, I rounded the trend. So that's the apparent power. So all I did here is I drew my power diagram, right? The real component, the reactive component. This is what I knew, the reactive component, right, of the power. I didn't know on any of the other two, but I knew the angle. Also from here, you can figure out the real power, right? The real power would just be note. Power equals S cosine 70. Oh, I drew a 70 here, and no, that's God, 75. Right. So once you know S, or you can use a tangent function to get it. Right. Tangent 75 is Q over P. So P is going to be Q over the tangent of 75. Part C, the RMS voltage. So we have the equation for RMS voltage. Oh, I don't have it with respect to Z here. I was going to use that because we have the load. Oh, I got to add that equation in here. Is it? Hold on. Let me see if it's in the list of equations at the end of it. It is not. That's why. Yeah, because it's not in that table. Anyway, it is this equation, 11.46. So these are the equations I added to the slide from 1151. We're going to use VRMS over the magnitude of Z. Well, even that was a complex conjugate one. Well, anyway, S equals VRMS. So because we're using the S and not, if we use the vector, we need the complex conjugate. But because we're not using the vector, we're using the magnitude, right? S, the apparent power, is VRMS squared over the magnitude of Z. And this gives you, if you solve for VRMS, you wind up with the square root of S times the magnitude of Z, right? And the magnitude of Z is 250. I'm going to expand this out to VA instead of kVA. So I've got 103,500 VA. And Z is the 250 for the top there. $103,500 times 250.5, 5086. I don't know, round it to 5087. This is actually voltage. So we'll just write that down here. VRMS is 5,087 volts. This is not the max voltage, right? This is the RMS, the root mean squared voltage. All right. We got one more section and one more problem. We can finish this today. If you're on board, we'll finish it. And that way, I know you have a test today. I was going to try to give you some time, but would you like to just finish this up today and have basically Thursdays either no class or you just drop by if you have questions? It's a poll. I'm sure by the time I finish this poll, I've wasted all the extra time. All right, so we're gonna. It looks like most people. All right, just one person said no. All right, let's finish this today. Power factor correction. This is fairly basic. There's one equation here to know. The point is that most loads, right, your washing machines, air conditioners, motors, particularly motors, right, are inductive. and they have a lagging power factor, but they're fairly low for residential stuff. You can change the load, but you can't change the power factor unless you alter somehow the voltage or current to the load, right? And this is called power factor correction. And so how does that work? Well, if you have a load like an inductor, you can add a capacitor in parallel with that load, and you can adjust the phasor diagram. So what does this do? This basically, you go from this is your inductive load, to a capacitor. You add this in parallel, and it basically brings the, notice the load current and the capacitive current draw a total current, which is now at a smaller angle. And this improves the power factor, right? Because the power factor is based on the angle, right? So the closer this angle gets to zero, right, the better your power factor is. So typically you're adding a capacitor with the point here is the same supplied voltage, the current draw is less by adding the capacitor. And think of that physically. What's the capacitor doing? It's helping to sort of jumpstart, right? It's providing it's providing some power, right? Power companies typically charge for larger current, or charge more for larger currents, because for them it's a larger power loss. Oh, I think this is where I had the equation. Remember, P equals I squared R. So the more current you have, right, the power goes up significantly, right? It goes by the squared. And the power factor correction is a benefit to the power companies and the consumers, really, because you can size things correctly. If you choose a suitable size of the capacitor, you can bring your power factor to unity, which this is ideal, right? It's not actually going to happen, but let's look at how this works. If you draw out your original apparent power, right, or complex power, because it's a vector, and then you want to get down to a lower complex power, right? You've got two different angles. You've got your original phase angle, and you've got the phase angle you're getting down to by adding a capacitor. And that can be represented by this diagram here. You're trying to make up this difference, QC, right, to drop that difference. So we want to decrease our reactive power by, say, QC, right? We can use this formula here. Capacitance is QC divided by omega VRMS squared. And this is just, QC is just P time power times the tangent of phi1 minus phi2, right? Because remember we said tangent relates P and Q based on the angle. The real power is not affected, right? It's all in the reactive power. Typically, like I said, most loads are inductive, so you use a capacitor to correct them, but you could do the same thing with a capacitive load. You could, if you had a capacitive load, so that's something down here, right? You could adjust that with an inductor and get the same type of value. All right, so find the value of parallel capacitance needed to correct a load of 140 kVAR at 0.85 lagging power factor to unity, meaning 1, right? So they want to bring the power factor from 0.85 lagging to 1. Assume the load is supplied by a 220 volt RMS 60 hertz line. So and we're going to need that 60 hertz because of the omega, right? Let's go down here. Oops. Let's do this. So the general formula is capacitance is QC divided by omega VRMS squared. Now, what's QC? Recall QC is Q1 minus Q2. Now, what we want to do is I'm gonna graph this out. We've got a load of 140 kVAR, right? That's our reactive power. So that's over here. This is Q1. And our real power looks like this. And so our apparent power looks like this, S. We don't actually need theta here, but we could get it by, oh, that's right. I wanted to show you, this is lagging, right? Current is lagging, so it's a positive theta. Theta is positive due to lagging current. Q2, we want to bring this down to 0, right? We want Q1 to go to 0, or Q to go to 0. So Q2 equals 0. That's what we want. So the capacitance is going to be, QC is going to be Q1 minus Q2 over omega VRMS squared. Now, omega, don't forget, omega is in radians. So we have 60 hertz, or radians per second, 2 pi radians. This gives us 120 pi radians per second, right? That's our omega. Q2, we already said, is 0. This is a desired, right? So capacitance is going to be, we got a kilo VAR, right? So 140,000 VAR, right? The reactive power. We got the 120 pi, 1 over, or basically 1 over seconds. And then we've got 220 volts squared, right? That's our 220 volt RMS. If you do this math, you're going to wind up with a capacitance equal to 0.00767 farads. So this is equal to, we can do millifarads, right? 7.67 millifarads. So if you put a capacitor in parallel with this particular load, and the capacitor is 7.67 millifarads, you're going to drop the power factor basically to, to 1, right? Cosine of 0. The only other stuff here is just a few slides. Conservation of AC power, right? Conservation of energy applies to both, DC circuits and AC circuits. This applies to real and reactive power, so conservation of real and reactive power. Apparent power is basically the vector product of those. So you have to take the individual ones, conserve real and reactive power, but apparent power is still got to be calculated by the vector. But complex power is a vector, right? So you can add that up. It's the magnitude that you have to just worry about. This is just going into applied stuff, which is not really, you don't have to worry about this for the test training, but it's practical applications, right? The power can be measured by a watt meter. It just tells you how a watt meter works. And the point here is that the coil is designed with a low impedance and it's connected to the series with some kind of load, right? Or it's connected in series with a load. So this is your watt meter here. The voltage coil is designed with a very large impedance and is in parallel with the load, right? So this is the watt meter, your current coil and your voltage coil. This is how a watt meter works. Yeah, this is just going into, again, I'm not, this stuff's just more of a point of interest. All right, we've ended here. This is it for chapter 11. So let me stop the video here. And if there's any questions,